Okay, I'm currently recording. So if you guys need a copy, yeah, you're welcome to record if you want to. That's fine. Um, yeah, if you guys can't make this session for a good reason, like you have sports practice or something like that, just let me know, and I'm happy to record and send you a link to the recording so that you can still participate.
Says
Also,
when we click it that you have to give us permission on Zoom.
oh, okay.
So I don't know. Yeah.
Hmm. I don't really know how to do that. So, uh, okay, how about this? If you want a recording of this, just email me. I'm recording it right now, so um, yeah. If you want a recording, just let me know. Okay. Okay, let's look at 130, or excuse me, 138. Was that Sophie that asked that?
Yes.
Yes. Okay. Thanks for that, Sophie. That's almost always the first question that comes up in recitation for this chapter. It's a doozy. Wait a minute. Here we go. Okay, number 138. Hi, Taylor. Welcome. Okay, so basically the preamble to this is in 1999, scientists discovered a new class of black holes, yada, 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 blah, 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 with 100 to 10,000 times the mass of our sun that occupy less space than our moon, blah, blah, blah. So all of that is just ancillary information. Don't let it confuse you. Suppose that one of these black holes has a mass of 1 times 10 to the 3 suns. So mass of black hole is equal to 1 times 10 to the 3 suns. Now, how many sig figs are in this?
Infinite?
No, this isn't an infinite number because it's giving you basically it's saying that through the exponential notation that it's giving, this is not actually going to be considered a whole number. You could probably argue that it is, but I don't think so. I think that this can be considered to be actually a decimal number. So in effect, it would only have one significant figure. But you could effectively argue that it has an infinite number, for sure. Okay, so I'm going to say that it's 1 sig fig. You might find a different, and that's okay as long as you argue your way through it. Oh, I should mention, by the way, in recitations, I'm basically just going through these problems by the seat of my pants. I think it's more fun that way. But whatever I solve in this is not necessarily the correct answer. Sometimes I make mistakes in my calculations, so you should always double check. Okay, I'm going to go through and show you kind of the logic of the problem, but don't trust my answer. You should always double check my math. Okay, I make mistakes just like everybody does. Okay, so it has mass of 1,000 suns and a radius equal to 1/2 the radius of our moon. So let's say radius black hole is equal to 1/2 radius of the moon. What is the density of the black hole in grams per cubic centimeter? So what we want to find at the end is the density of the black hole in grams per cubic centimeter. That's our goal. That's what we want to find. Now, density, as you probably remember from class, is mass per volume. Okay, it's a physical quantity of an object. Okay, it tells you the density of that specific thing. So here it goes, and it tells us the radius of the sun. We get further information here. The radius of the sun. Oh, here we go. Radius of the sun is equal to 7.0 times 10 to the 5 kilometers. And has an average density of 1.4 times 10 to the 3 kilograms. So density of sun equals 1.4 times 10 to the 3 kilograms per meter cube. Okay, so that's the average density of the sun. And it also gives us the radius of the moon. 2.16 times 10 to the 3 miles. Okay, actually, I'm going to go back on what I said. I am going to assume that this has an infinite number of significant digits, okay? And the reason I'm saying that now is because I realize that those sig figs are going to limit the entire answer because the one is the least amount. So I'm going to renege on that. And I'm going to say, actually, no, it probably makes more sense for that to be infinite. So I'm just going to assume that it's infinite and go with it there. And then these guys here are what's going to determine sig figs.
Hey, so is that the diameter of the moon instead of the radius?
Is it? Oh yeah, it is. You're right. Thanks. See, I make mistakes. You got to catch them. You got to catch them. Okay. So let's see. 2.16 times 10 to the 3 miles. Okay. So our final goal is the density of the black hole here. So what do we need to know in order to get to the density of the black hole?
The mass and volume.
Yeah. So we need the mass of the black hole divided by the volume of the black hole. Okay. Let's see. Let's do with mass first. Let's find the mass of the black hole first. So mass of the black hole, and we want this to be in grams per cubic centimeter. So let's find the mass of the black hole in grams. How do we start this? Well, we're given a piece of information up here that the mass of the black hole is equal to 1 times 10 to the 3 suns. Okay, so it's just 1,000 suns that make up this mass. But we're not given the mass of the sun. We're given the radius of the sun and the density of the sun. So how can we convert that into the mass of the sun?
Use the density formula.
Yeah, so if we use density, so to figure this out, we have to say, okay, mass of the black hole is equal to 1 times 10 to the 3 suns. And the sun is going to be equal to the sun density here, or the sun mass is equal to the density times the volume. So to get the mass of the sun, we need to multiply the density that we're given by the volume that we can calculate. Okay, so we're given the density. We know the density of the sun. We just have to figure out the volume of the sun. So volume sun is equal to, does anybody remember the formula for the volume of a sphere?
4/3 pi times radius to the third.
Yep, that's it. 4/3 pi r cubed. That is the volume of any three-dimensional sphere determined by the radius. Okay, and we're actually given the radius of the sun. I think that's the radius. Let me double check. Yeah, it's given to us as the radius of the sun. So we can directly plug this in and get the volume of the sun. But first, I want to take the number that we're given, which is 7.0 times 10 to the 5 kilometers, and I want to change that into centimeters. Okay, so before I even calculate the volume, I want to change it into centimeters instead of kilometers. Okay, so to do this, we have 7.0 times 10 to the 5, is that right? Yeah, kilometers. So this is our sun. And I want to change this into centimeters. How many centimeters are there in 1 kilometer? Let's do it easier. How many meters are in 1 kilometer?
1,000.
Yeah, 1,000 meters. So to build this conversion factor, we have 1,000 meters on the top and 1 kilometer on the bottom, like this. Okay. Then kilometer cancels out here. Now we have the radius of the sun in kilometer or in meters. So now how many centimeters are there per meter? How many cents are in a dollar?
100.
100 centimeter per meter. Okay. And of course, these are all whole numbers here. So they have an infinite number of significant figures. So our final answer will be 10 to the 5 greater. So that would be equal to 7.0 times 10 to the 10 centimeters. Yeah, that's right. Yeah. Does somebody double check that? I'm pretty sure that's right. So that's the radius of the sun in centimeters. Okay. Now all we have to do is plug this back in to the volume up here, and we get the volume of the sun. So now we have volume sun is equal to 4/3 pi times r cubed, 7.0 times 10 to the 10 centimeters cubed. Okay, so then the volume of the sun is equal to, let's see, can somebody plug that in a calculator? That'd be a lot easier. It'd be like 4 times 35 times.
Dr. McDonald,
Yeah.
is it when I was working through this, I did all of those conversions at like right before the last step of the whole problem. Is that okay, or is it easier or better to do it earlier?
So yeah, it's totally fine. You can do the conversion whenever you want. The reason that I'm doing it right now is because it's a cubic. We're ending up with a cubic value here in cubic centimeters. And it's a lot easier to convert, in my opinion, or at least to avoid losing track of the cubic if you do it in the very beginning. So this is just the way I do it. You can do it at the end just as easily. Okay, so somebody plug that in a calculator.
I got 1.4 times 10 to the 33rd power.
1.4.
I second that.
Yeah, that makes sense. That's the right magnitude. So what is it? 1 point what? 1.4?
Yes.
Can you give me a few more digits?
1.436
times 10 to the 33rd centimeters cubic. Okay, that's the volume of the sun in cubic centimeters. Hey, by the way, I don't know if you guys have ever heard this, but a cubic centimeter is a cc. So when you go to the doctor and they're like 500 cc stat, they're talking about cubic centimeters. And this is actually 1 cc is equal to 1 milliliter for water. Whoa. Okay, so yeah, there we go. We have 1.4 times 10 to the 33rd cc's of volume here, cc's of sun. Don't inject that into you. That would probably burn you quite a bit. Notice how here I am not rounding the answer, okay? I'm just keeping track of the significant figure here. And that sig fig is determined because we have 1, 2 sig figs in 7.0 times 10 to the 10. Okay, so I'm not rounding it yet. I'm just keeping track of the sig fig with that underline. Okay, now we have the volume of the sun. Now we can calculate the mass of the sun using this formula here. So if we just multiply the mass by if we multiply the density by the volume, we get the mass. So mass of the sun is equal to density of the sun multiplied by volume of the sun. Okay, so the density of the sun is given to us. Okay. So actually it would have made more sense if we had waited to do our unit conversion. We're gonna have to convert again. That's okay. Let's go ahead and convert the density into the density of the sun into into kilograms per centimeters cubic. So right now the density of the sun is equal to 1.4 times 10 to the third kilogram per meter cubed. Let's convert that into kilogram per centimeter cubed. Oops. Okay, the way that we convert this from meters per meter cube into per centimeter cube is we have to multiply it by the correct conversion factor. And the conversion factor here is meters to centimeters. So I have 1 meter on the top. I want to get rid of the meters on the bottom. So I have 1 meter on top. And then on the bottom is 10 to the 2 centimeters. Now, this is really important here. You have to cube the whole thing. Okay, you have to cube the whole thing. And when you cube the whole thing, you end up with one cubed is just 1. So it's 1 meter cube is equal to, when you cube another exponential, or when you raise an exponential to another exponential, you multiply the factors together. So this becomes 10 to the 6 centimeter cubed. Okay, make sense? Now we can just X this out. So we have now, oops, this is kilogram, my bad. Now we have 1.4 times 10 to the 3 divided by 10 to the 6 gives us a 10 to the minus 3 kilogram per centimeter cubic. Does that make sense to you guys?
So would you keep the 1.436 when you're multiplying that, or just go ahead and do the 1.4?
So in my book, it just gives it as 1.4. There's only 2 sig figs.
Gotcha. Okay.
Oh, I'm sorry. Oh, okay. You're talking about the volume here. This is actually the density. I'm pulling the density out of the book, this number right here, and it's given to me as 2 sig figs.
Okay.
I'm going to use this value in just a little bit with this up here to get the mass, but it's not the same. Okay, so now we have the same unit centimeter cubic and centimeter cubic here. Now I can get the mass of the sun by multiplying the density, which is here, multiplied by the volume, which is there. So 1.4 times 10 to the minus 3 kilograms per cubic centimeter multiplied by 1.436 times 10 to the 33rd centimeters cubic. Centimeters cubic cancels out, and I get a final answer in kilograms, which is great because that's the unit for mass, and that's what I'm going for here. So now I have 1.4 times 10 to the minus third times 1.4 times 10 to the 33rd. That's going to be approximately 3 times 10 to the 30. Maybe somebody can calculate that real quick. Beat you to it. It's 2.01. And I'm going to keep the 2 significant figures that are basically limited by here and here. Okay. I'm going to keep 1 digit beyond just to keep from rounding errors happening. Okay, so this is the mass of the sun, right? Now we can get the mass of the black hole, because the mass of the black hole is equal to 1,000 times the mass of the sun. So the mass of the black hole is equal to 2.01 times 10 to the 33 kilograms, because it's 1,000 times this number up here. Okay, make sense? So that's the mass of the black hole. We need the final mass to be in grams. So let's go ahead and do that unit conversion right now. Let's multiply this by 1,000 grams per 1 kilogram. Kilograms cancel out, and we end up with 2.01 times 10 to the 36 grams. Okay, that's the mass of the black hole that we're going to come back to in just a second. Okay, so whenever I get to an intermediate answer, I like to circle it just so I can remember where the heck it is. Okay, so we have the mass. Now we need the volume of the black hole. And we're given a few clues to get that. We're given the radius is half the radius of the diameter of the, wait a minute, what is it? It's half the radius of the moon. Yeah, So the radius of the black hole is half the radius of the moon. We have to figure out the radius of the moon in, let's do centimeters again, just for the heck of it. So here we go. This is the diameter of the moon is what's given to us. Diameter of the moon is equal to 2.16 times 10 to the third miles. I don't know the conversion factor between miles and kilometers. I can't remember what it is. But I know how to go from miles to feet, and then from feet to inches, and then from inches to centimeters. So if anybody knows, that's a huge roundabout way to do it. If anybody knows the direct conversion between miles and kilometers, that'd be awesome. Yeah, Stacey. Can't hear you. I can't hear you.
It says.
Okay, I can hear you now.
It's 0.6214 miles per kilometer.
Okay, 1 kilometer is equal to how much?
0.624. 214. I'm sorry.
214. That's okay. We can squeeze a 1 in there. Miles per kilometer. Okay, this is our conversion factor. This makes it a lot easier. Thank you very much. So then we'll just cancel out the miles there, right? And we end up with, let's see, 2.16 times 10 to the 3 divided by 0.6214 kilometers. So somebody calculate that real quick and shout out the answer. Actually, whoever calculates it, go ahead and go divide it by 2 because we need the radius.
Is it 1.738 times 10 to the 4th?
1.738. Did you divide it by 2?
Yeah.
Awesome. 10 to the, wait. Really?
Yeah, I think that's what I got.
I got 10 to the third.
Yeah, I would think 10 to the third here.
Okay. Oh, no, I added in a 0. Yeah, you're good.
Yeah, is it a 3? Okay, cool. And let's see, let's do sig figs here. So we're given 3 sig figs up here with the moon. And since we put in more than 3 sig figs here, we're good. We're not limiting ourselves with our conversion factor, even though it is a decimal conversion factor. So our final answer here should be to the third sig fig. Okay, and that is kilometers. So I want to get this into centimeters so that I can, oh wait, no, this isn't the radius of the moon. This is now the radius of the black hole because I divided it by 2 here. Okay, so I took the radius of the moon, which is here. Oh no, wait, that's the diameter. Never mind, that is the radius of the moon. It's easy to get confused here, people. Okay, let's divide that by 2 again and get the radius of the black hole. Let's see. Shout it out if you got it.
Is it 8.69 times 10 to the second?
Yeah, that seems right. Can you give me one more digit?
0.
Okay, cool. All right, so this is the radius of the black hole. Now we can use this value to calculate the volume of the black hole using the same thing that we used earlier. We have the mass of the black hole, we just need the volume, and then we can figure out the density. So we have one last step. We need to figure out the volume of the black hole, and that is going to be equal to 4/3 pi r cubed, which is in this case, r is equal to 8.690 times 10 to the 2 kilometers. Actually, let's go ahead and switch that into centimeters cubic. Scratch that. Zoop, 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 zoop. Dude, I like this because it's a lot easier to erase than the blackboard. Blackboards are such a pain to erase. Okay, let's actually put this into centimeters instead of kilometers. So the conversion factor from above was 10 to the 5 10 to the 5 centimeters per 1 kilometer. Okay, so then we have this, the radius of the black hole in centimeters now is 8.690 times 10 to the 2, times 10 to the 7 kilometer, or centimeters. Okay, that seems right. Okay, now let's do the volume. So volume is equal to 4/3 pi r cubed, and in this case, r is 8.690 times 10 to the 7 centimeters. And then cube that, and we get our volume of the black hole. Somebody plug that in.
Is it 2.748 or 9 times 10 to the 24th?
Let's see, 7, 14, 21. That seems like the magnitude. Can you say that again?
2.748, and then there's like 3/8 times 10 to the 24th.
Yeah, that seems right. Okay, and this has 3 significant figures. So there is the volume of our black hole. And I'm going to put a little circle around that so that I can come back to it. Okay, so we have the volume and we have the mass. The mass we calculated above here is 2.01 times 10 to the 36 grams. And then we divide that by the volume of the black hole, which we just figured out, 2.748 times 10 to the 24 cubic centimeters. And we end up with, this has 2 sig figs, this has 3 sig figs. It's like 7.5 times 10 to the...
I got 7.31
7.31
times 10 to the 11th.
grams per cubic centimeter. Okay, let's do sig figs. So here we have 2 sig figs, and we get 2 sig figs from this guy here. Okay, so we get 2 sig figs, 3 sig figs from here. So that means that this final answer should be 2 significant figures. And so we end up with 7.3 times 10 to the 11 grams per cubic centimeter.
Where did you get the 2 sig figs?
That's from the mass of the sun up here. And that was determined by, let's see, so that ends up being 2 sig figs here. And the mass, or excuse me, it's from the mass of the black hole. And then the mass of the black hole is given to us by the mass of the sun. And let's see here, the density of the sun is what limits the sig figs here.
Okay, I got it.
The density is at 1.4 times 10 to the 3s. That's only 2 sig figs, and that ends up limiting it to 7.3. Does that make sense?
Yes.
Okay, so this, as you can see, this problem is just one huge unit conversion problem. That's all it is. And yeah, I mean, there's a lot of unit conversion that happens in it, and a lot of things that can go wrong if you mix up one of the numbers. But at the end, you should get a number that's pretty similar to this. Okay. Matter of fact, I can check this real quick. Hold on. Exactamento. That's right. The answer for this is 7.3 times 10 to the 11. Pretty neat. That's extremely dense.
Did you say it was 7.32?
7.31 was the 3 sig fig. So the digit after the 3 would be a 1. But we're not going to report that because it's limited to 2 sig figs.
Okay, yeah, I just had trouble with the like those sig figs at the end, I think.
Yeah. So the thing that I do to make sure that I don't mix up the sig figs is I always underline, like here underneath the 0, and that just helps me remember how many sig figs I have in the final answer. Because if you don't do that, it's really easy to get confused. Okay. Do we have another one?
I missed all of 52.
52. We didn't go over 52 yet. You want to go over 52?
Yeah, I feel like they're right, but I don't know.
I had struggles with 52 as well.
Oh yeah, these are temperature conversions. Okay, let's do one. So 52. Okay, so we're asked to convert 212 Fahrenheit to degrees Celsius. Okay. Okay, so what is the conversion factor for Fahrenheit to Celsius? Does anybody remember? Like, oh, here it is. So if we want to go from degrees C to degrees Fahrenheit, degrees C is equal to degrees Fahrenheit minus 32 divided by 1.8. Okay. Sig figs. Let's talk sig figs here. So this number here, I would say has an infinite number of sig figs because 32.0 is infinite. 32 exactly is defined as the boiling or the freezing point of water, which is where that comes from. The 1.8 on the bottom is a little bit more ambiguous. I'm not sure where that comes from. When you come to a case like this where the formula is ambiguous as to where the sig figs come from, the best option is to revert to the sig figs of the original problem or the original value. So in this case, I have 3 sig figs in the original number. So I'm going to go ahead and assume that the final answer is 3 sig figs, even though it's kind of ambiguous how many sig figs are in these two numbers in the conversion factor. Okay, so for 212 Fahrenheit, we need to rearrange this so we're solving for, oh no, we don't. We can just plug it in. Okay, degrees C is equal to 212 degrees Fahrenheit minus 32 divided by 1.8. And that equals to 180 over 1.8 equals 100. Okay, so this has 3 sig figs. That means that this final answer should have 3 sig figs. So I report it as 100 point, right? We have to put in that decimal to show that those 200, the 2 zeros are significant, or we can write it as 1.00 times 10 to the 2.
Which one will be right on the canvas?
I think either one is good, but this one for sure is good. I know that 100 point is in there. Okay, so that's A. There's a bunch of these, so let's go down and do B. Let's see, B. 22 Celsius to Kelvin. Okay, our conversion from degrees C to Kelvin is degrees C plus 273.15 is equal to Kelvin. So here I have 2 sig figs, so I take 22 and I add to it 273.15. I keep, this is an addition problem, right? So addition problem means that we keep the lowest number of decimal places. Now in this case, there are no decimal places, but we have on the other side of the decimal, this 2 here, okay, in the tenths place. When there's nothing on the right of a decimal and it's only on the left of a decimal, you keep the lowest value significant figure to the left of the decimal point. In this case, it's the 2. So now our answer has to be significant to the one or the tenths place or the ones place, excuse me. So our final answer would be 295.15. And this is the significant figure. Even though there's 2 here and 5 here, we end up with a value that is 295, which has 3 sig figs. Okay, that's B. Let's do C. 0.00 Kelvin to degrees Fahrenheit. Okay, for this one, we have to go from degrees Fahrenheit to degrees Celsius, and then from degrees Celsius to Fahrenheit. So let's go from Fahrenheit to Celsius. Oh, wait, no. Let's go from Kelvin to Celsius. So Kelvin to Celsius, we would subtract 273.15 from the number. So 0.00 minus 273.15 is equal to negative 273.15 Kelvin. Excuse me, Celsius. Notice that this is giving us significant figures to the tenths place. So that means that my answer has a significant figure out to that same decimal place. So I now have 5 significant figures in my intermediate answer here. So now we have degrees C. Let's convert that into degrees Fahrenheit. From above, degrees C is equal to degrees Fahrenheit minus 32 divided by 1.8. Now let's solve for degrees Fahrenheit. That would be degrees C times 1.8 plus 32 is equal to degrees Fahrenheit. Did I do that right? That seems right. Okay, so now we just have to plug in the numbers. Again, here, I'm going to assume that these are not limiting my significant figures. I'm going to assume that they have an infinite number of sig figs. So in this case, we have, I don't know, negative 273.15 times 1.8 plus 30, oh wait. Oh yeah, that's right, plus 32. Does anybody have that calculated?
And 59.67.
59.67.
459.
459. Okay, that makes sense. Negative 459.67. Okay, in this case, our sig fig is limited by this digit, so our sig fig should be here. So this is how we should report the number. And now I will grant you that this conversion into Fahrenheit and between Fahrenheit and degrees Celsius, the sig figs are extremely ambiguous because of this formula that we're given in the book. In the case where it's ambiguous, I would say that you should just go back to the significant figures that you're given in the original problem itself. Okay? And then let's see, last one. D. 2.735 Kelvin, 2 degrees C. Okay, this one's pretty straightforward. We just have to, whoa. Was that on my end? Sorry. Some weird noise. Okay, we just have to subtract 273.15 from this number here. And we get degrees Celsius. And that is equal to negative 272 something something. No, 271 something something.
It's 0.415.
270.415?
Yes.
Okay. And that would be good to, okay, so we have 3 digits out here. We only know 2 digits out here. So this is another one of those cases where the conversion factor is limiting us here. In this case, I would say actually that we should go out to the second digit. Because if you want to, you can look this number up to many more digits than this. So I would say in this case, if we use this number here, we're limited by the second digit there. Okay.
So like, what makes you distinguish like when you're able to like use the conversion factor to be the significant figure?
Usually you don't want the conversion factor to be the significant figure. If you're given the conversion factor in the problem, for example, in 138, where we're given conversion factors, then we're limited by the numbers that we're given. But in this case, this is such a common constant that people talk about that it would be very easy to just Google conversion between degrees Celsius and Kelvin and get much more numbers on that. And it, actually, now that I'm thinking about it, this might be exact. I can't remember though. Yeah.
Dr. McDonald,
Yeah.
on part B, you had said it's 295. Do we need to put a decimal point after that like we did for 100?
No, because it's a non-zero number.
Okay.
You only need to put the decimal after a 0 because otherwise it's ambiguous.
So do you always use the lowest amount of significant figures?
I don't know. That's a very open-ended question.
I just wasn't sure.
Do you have a specific example or?
Like how you said before, where it's like 2.735 and the other one only goes to 0.15 and you use the smaller amount.
Yeah, so this is just one of the rules of sig figs. So when you do a subtraction like this, you only keep to the second digit beyond the decimal. But I think what you're asking is, how do you know to think of that as being the limiting factor? Like, why couldn't I just go and say, hey, I want to find that to a higher amount? Is that what you mean?
Yeah, like why didn't you use the other one instead?
Yeah, this is a good question. I'm basically just limited by what the book provides for me for this value right here. I could just as easily find this to a larger or to a more precise value. But since this is what's given in the book, I'm choosing to use this precision value, which, since it only goes out to 2 decimals beyond, I'm limited to 2 decimals beyond in the result.
Oh, okay.
Sig figs are kind of chemistry professors and chemistry teachers like to pretend that they're a definite thing, but they're not. You can find so many cases where you can argue one way or another. And I'm totally open to you guys coming to me and arguing. If you think you got a sig fig correct, and you can show me why you think it's correct, I'm happy to hear that. Okay.
So since that value is from the book, could you have used that technically for like C as well?
Let's see, C. Yeah, I mean, yeah, you can with C, you can argue either way because I have no idea where these numbers actually come from, and I don't know if they're, and you don't know unless you look it up, if they're exact values or not. I'm guessing that they're not, especially the decimal here. I'm guessing that that's not an exact value. So you could absolutely use that to argue that the number should be limited to 4 sig figs, right? Because in this case, well, you'd have to do this multiplication first. I don't know how many sig figs it would limit it to. You'd have to check that. But yeah, you could certainly use that argument for sure. Because in this case, I think it's completely ambiguous. Okay. Let's see. We have 9 minutes left. Anybody got something else?
I have another question.
Sure.
So on number 38 and 42, where it's about the pure substances or the mixtures,
Yeah.
when I put that in, they said that all of them were wrong.
Mm-hmm.
But like I looked them up in the book and they said that they were right. So I just didn't know if I should like put it in differently
That
or
happened
not.
to me too.
Yeah, I think that this is my fault. This happened to probably about 90% of the class. So I am going to be going through all of these quizzes to make sure that things like this don't happen. Essentially, I want to make sure that the format that you're putting in isn't counting it wrong. So I saw a lot of people putting in things like, for example, element, comma, space, pure. Okay. And the way that I had it formatted in the question was to get the answer correct, it had to say instead pure element. Okay. So a lot of people put in stuff like this, and this is completely, totally, and utterly correct. And so is this. I mean, either way you put these in, it's correct. So it's just the limitation of the program that's actually grading this. And I guess what I can say is if you think that they're correct, don't worry about it because I will be going through these and double and probably triple checking them and changing your grade.
Could you go over 34 and just like kind of explain like laws and observations and theories?
Sure. Number 34, let's see. Okay, so this is asking us to classify each statement as an observation, a law, or a theory. Okay, letter A, it's saying that chlorine is a highly reactive gas. Chlorine is a highly reactive gas. So what is this actually saying? It's saying that it's giving some sort of reactive property of chlorine, right? It's saying that if I take chlorine and I add it with other stuff, something cool is going to happen. Okay, it's highly reactive. It's going to react with stuff. Okay. Do you think that this is something that is predicting the future, perhaps? I would say that it is, because it's saying that if you ever put chlorine with other stuff, it's going to be reactive. So I would classify this as a law. It's a collection of observations. So it's a series of observations that were summarized into one statement that predicts the future. Okay, I keep doing that. Letter B. If elements are listed in order of increasing mass of their atoms, Their chemical reactivities follow a repeating pattern. Okay, again, this is basically telling us what different substances are going to act like in the future, or it's predicting some action, not necessarily in the future, it's predicting some action. It's predicting how particular elements are going to react. So this is necessarily then a law because it's summarizing a whole bunch of observations, basically the observations that how all of these elements that are arranged like this react and telling you how they're going to react in the future. So this is also a law. Okay.
Can we go back to that first part?
Sure.
I was just wondering why it's not like a singular observation and then there's more than one.
So which one, A or B?
A.
A. Because you can't say, if you have one observation, you can't say that chlorine is a highly reactive gas.
So the observation is not that chlorine's a highly reactive gas.
No, this would be a law because you can only make a statement like this if you have multiple observations, and not only that, it's actually predicting the future.
Okay.
So an observation, right? So if I get rid of this and I say, how can I change this statement to be something like an observation? An observation would be something like chlorine and sodium react to form sodium chloride. Okay, that's an observation.
So it's like a specific instance, and not like.
Exactly. Yeah, exactly. Yep. And the fact that this is really general, basically it's saying that chlorine is highly reactive. It means that it's going to react with anything, really. And because it's so general, that must mean that many observations went into it, and that therefore means that it's a law and not just a singular observation. And the same is true for B. Okay, so C, for the same reason that chlorine is a highly reactive gas is a statement of law. It's a law statement. That means that saying neon is an inert or non-reactive gas is also a law, okay? So this, again, is based on a series of observations saying, okay, well, what if I put neon with sulfur? What if I put neon with carbon? What if I put neon with anything? And I see no reaction. The sum of those observations tells me that neon is an inert gas. Okay, so it's a series of observations that are kind of compacted into one thing. So that means that this would be a law as well. And then for D, okay, so D is saying the reactivity of elements depends on the arrangement of their electrons. This is giving me a Y. This is saying when elements are reactive or when they're inert, it's all dependent on the way that their electrons are arranged around the atom itself. So I'm saying this is happening because of, or this is happening due to some physical property. And since it's answering the question of why, this is a theory. Okay? Does that make sense?
Yes, thank you.
Yeah, sure.
Can you do 64 real quick, please?
Let's see. I have a minute and a half. Let's try to do this real fast.
Thank you.
I'm just kidding. I'm kidding. Yeah, we'll do 64. Okay, so how many, this is asking how many 1 centimeter cubes are needed to make a, what's the question? Cube that is 4 centimeters on edge. Okay, how many 1 centimeter cubes would it take to make a 4 centimeter wide, long, and tall cube? So let's draw a cube here to kind of visualize this. Oof. Yeah, that looks pretty bad, but you get the idea. Okay, so we want this to be 4 centimeters wide. And we want it to be 4 centimeters tall because it's a cube. And we want it to have a 4 centimeter width because it's a cube. So all sides are going to be the same. And if we kind of draw in the cubes here, so let's see, one, oh, that was really bad. Okay, so there's 4 rows of cubes there, 4 here, and then we do the same here. Okay, so we're making a cube, a big cube that's composed of a bunch of smaller cubes. And so the question is, how many cubes do we have to put together? We could break something like this out and count these things individually, but it's a lot easier to just take the length times the width times the height and calculate the volume of this shape here. So we know that each side is equal to 4 centimeters. So we can say that the total volume is equal to 4 times 4 times 4 is equal to 64 centimeters cubed, which means that you need 64 cubes. I like this question because the answer is the same as the number.
Yeah, that's what I saw. And I wasn't sure if that was right.
Yeah, 64. That's correct. Okay, guys, I'm going to sign off for now. Just remember that when, if you submit something and you really think that it's correct, just remember that I'm going to be going back through these, the quiz answers, and I'll be fixing anything. And if even after I fix it, you still think something is correct, you can absolutely 100% always email me, come and talk to me, whatever. We'll figure something out. And if you can convince me that you are correct, then I'll give you points back. Okay? Cool. Well,
can I ask one question, like quick?
Yeah.
So if you're converting from like centimeters to meters, is that an exact like significant figure thing? Infinite
Yes.
number? Okay.
Yeah. If the definition for a centimeter is that there are exactly 100 centimeters per exactly 1 meter. So that conversion wouldn't affect your sig figs at all.
Okay. Thank you.
Yeah. Okay, guys. I hope you guys have a good night. I'll see you all either tomorrow if you have lab or Friday if not. Take care.
Thank you.
Thank you.
Yeah.
Thank you.
You're welcome.